Hi, in this video I'm going to show you one of my latest projects, a completely integrated standalone GSM platform. I'll start by making a short intro about GSM Communication, just some very basic stuff. So I'm going to walk you through a few short slides and then we're going to get to work and see what this board can do. I also want to talk about how to make use of GSM and GPRS communication standards and how you can integrate them in electronic projects, because the applications are virtually everywhere. GSM stands for Global System for Mobile Communications, and it has been around for almost 25 years. It constantly evolved since the beginning of the 90s, and it's now at its fourth generation, which is known as 4G or LTE, and this is still being further enhanced as we speak. GPRS stands for General Packet Radio Service. It came out as an extension for the second GSM generation, and it makes it possible to transmit data over 2G and 3G networks. Now let's take a look at how the communication is being done. GSM network operates as a cellular network, meaning that an area is divided into multiple cells, and each one of these cells has a radio station, which is called the base transceiver station, or the BTS. Now, when you are moving inside this area, your phone or the mobile station is always trying to acquire the best signal possible, and this is being done by constantly scanning and comparing the signal strength of each visible base station, and then jumping to the strongest signal source. Everything that happens behind the base stations is called the core network. And that's basically all the switches, cables, all that huge infrastructure that makes the long-distance communication possible. And if you wonder how big this infrastructure is, well, let's just say that at this moment there are 7 billion devices registered in GSM networks, and I guess that says everything about it. So I started quite some time ago to think of different ways for making use of this huge infrastructure, and basically that's what drove me to design this board. In the past I used to hack into cell phones and try to interface them with a microprocessor or directly with a computer and send AT commands. Some of these cell phones were actually very simple to interface with. They used in some cases standard UART for communication with other devices or for debug purposes. And once you found these pins, you pretty much can access some of the phone's functions. I also played with some dedicated modules, I guess from Siemens, but they were pretty expensive back in those days. A few months ago I found this chip. Actually it's a module. It's fairly small sized, 24 by 24 millimeter, 3 millimeter thickness. It's packing a lot of nice features and you can see them in this slide. It's a quad band GSM module. It works on 850, 900, 1800 and 1900 MHz. It features a multi-slot class 10 GPRS, supports TCP/IP, fax, packet broadcast control channel. It supports pretty much all the SMS standards. It can interface with both 1.8 volt and 3 volt SIM cards, so there's an internal DC to DC converter and some level translation for the SIM card signals. It has some nice audio features like echo and noise suppression, 2 serial ports, one for communications and the other one designed for debug and firmware upgrade. It has an internal ADC which can be used to monitor the supply voltage, an internal temperature sensor. It supports an RTC, however I used a dedicated chip for the real-time clock. It has different operational modes which can be used to efficiently control the power consumption. Most of the hardware control functions can be also implemented in software by using dedicated AT commands. So once again, a very nice module, and I bought like a few of them and then started to design my own board around it. And I didn't want it to design just an extension board like a shield or something, but rather to make a standalone system, more like a GSM terminal with a display, manual controls, and ways to interface with it from the outside world. And here's the prototype board I've designed. This is version 1.2, so I corrected pretty much all the issues I had on the first two versions. Here's a close-up of the board. This is the power supply circuitry in this corner. So basically this converts the DC input, which has to be somewhere around 5 volts, at minimum 2 amps. The current draw is actually a lot smaller than that, but when the GSM module is working in burst mode, you get these 2 amp spikes, and the power supply has to be able to deliver that, because otherwise the system would stop working properly. That's the GSM SIM900 module itself. Here is a SIM card connector, and you can use an adapter if you have a micro SIM card. This is the GSM antenna connector here. I don't know if you can actually see this on the video. There is a micro strip here for matching the 50 ohm impedance of the antenna. And I've tested this system with 2 different GSM antennas. This is the first one. It's foldable. And this is the second type. A little bit smaller, not foldable, but this one here is better. I get better results, better signal strength when using this. Here is the microcontroller that I use to control everything on the board, including the SIM900 module. It's an 80 mega 128A, so 128A. It has a lot of flash, 128 kilobytes of flash, 4 kilobytes of static RAM, 4 kilobytes of EEPROM. It has a lot of I/O lines, and I used almost all of them. A decent ADC, analog to digital converter, an analog comparator, PWM outputs, 4 timers. It runs up to 16 MHz, which is more than enough for what we need. I actually used an 11.0592 MHz crystal to clock the AVR, because that's a better frequency when you are using the UART communication. It minimizes the errors. Here's the audio input and output. So basically here's where I'm going to connect the microphone input and the speakers or headphones output. This is the USB connector here. It's a mini USB connector, and I used a dedicated FTDI chip to implement the USB communication with the AVR. That's a small piezo speaker here to generate some noise. Here is the RTC section. This is the RTC chip that I used, and a standard 3 volt battery as a voltage backup. That's a reset switch for the AVR, and these are 3 programmable hardware keys. And obviously this is the display here. It's a 2.8 inches, 240 by 320 pixels. It has a touch screen, and I'm driving it using SPI. There are 5 LEDs on this board. This one here shows that the power supply is connected. The second green one here shows that the SIM900 module is powered. This voltage regulator here has a control pin, so I can actually switch the power on and off for this SIM900 module in software from the AVR. The third LED, it's a blue one here. It says network on the PCB, and it blinks differently if the SIM900 module is connected or not to the network. So basically you can see if you lost connection with a BTS, for instance. The fourth LED here, it says COM on the PCB, and it indicates the USB activity. And the last one here, I use this for ringing indication when there's an incoming call or something. Here's the ISP header for flashing the AVR. Here are the debug pins, if you remember that second UART of the SIM900 module. These jumpers here, I use them to select between if I want to use the USB or I just want to access the I/O pins or flash the AVR, because these pins are shared on the Mega 128, the port E1 and E0. On this 10-pin connector here, I have ground, VCC, and 8 I/O lines. I defined them as 4 inputs and 4 outputs, but you can do whatever you want with them if you write your own software. The back of the board, there's only the 50-pin display connector here, and that's pretty much it. I'm going to connect the power supply, put a SIM card into it, and I'm going to show you the software I wrote for it. This software only shows some of the functions of the GSM module. I didn't have time to implement all of the stuff like GPRS or TCP/IP stuff, and I also reach like 99% of the AVR's flash for this firmware. So I'll need to either write a new firmware for these separate functions, or it also crossed my mind to design a new version, maybe use an ARM processor, maybe some external RAM, and perhaps run Linux on it, or Android. We'll see. First thing I do is to connect the SIM card. The SIM900 module will accept any GSM SIM card. There's no such thing as carrier lock, and it doesn't matter if you use a subscription or a prepaid SIM card. Just press it gently and then lock it in the position by sliding this metal plate to the left. Now the antenna. And now I'm going to connect the headphones. I'm using these standard headphones with the microphone on the cable. And this red connector is for the microphone. The green one is for the headphones. The USB cable is just a standard mini USB connector. And now it's a good time to make sure that these jumpers here, jumper 3 and 4, are correctly set. So if we look on the back side of the board, jumper 3 and 4, and I want to use the onboard USB, so I got a short pin 1 and pin 2. And it looks like they're in the right position here. If not, just remove them and place them right. The DC input supply goes on this connector here. Just watch for the right polarity. In my case, the red wire is the positive one and the brown wire is the ground. And that's it. Now we're ready to power on, and I'm gonna open a terminal window on my computer, and we're gonna keep an eye on that too as we watch the board. The power is now on, and I manually hold the AVR in reset by keeping this reset button pressed, just to show you guys what happens when it starts to boot. As soon as I release this key, the reset line goes high, the code starts to execute. So I initialize the display and you're gonna see a splash screen, and at the same time I initialize the UART, so it's gonna start talking on the USB, and then it will switch the power on for the GSM module, and it sends the GSM initialization commands. Also watch the network LED, because it will blink fast, and once it blinks at a slower rate, that will be the indication that the system has successfully authenticated and is registered on the GSM network. And here we go. So basically the system is now up and running. The GSM module is registered on the network, and I'm gonna focus on the display right now. I readjusted and repositioned the camera, and I just hope the focus is good enough and you can see the display. Basically this is the main menu, and from here you can launch all these applications. Like I said, this software is more like a proof of concept to test and demonstrate the system's capabilities, and the way it looks and what it does is just my own approach, and it can be done in a million other ways if you want to write your own software. So anyway, let's start with the phone application. I can use my finger to touch the display, however I don't want to leave any marks on this brand new display, and it doesn't look very good on the camera either. So I'm going to use this pencil. The phone application, a couple of things to mention here. In this corner there's the signal strength. In the original software I had a phone book. It was located on this side, and making a phone call was easier. I just had to scroll through a list and pick a name. I made all these applications separately, and when I started to put everything together for the final firmware, it would override the bootloader section. It wouldn't fit the AVR's flash. So I had to optimize the code, and I removed a couple of things. Let's make a phone call. And I can either remove a character at a time or the whole number. Now let me just enter the number. And now I'm going to press call. And this other cell phone here should receive the call in a moment. Here it is. I'm going to take the call, activate the loudspeaker, and maybe you can hear on the video. Now I'm using this microphone. Testing, testing. The audio quality is very good. It's crystal clear. That noise filtering they promised in the datasheet is really working. The noise you just heard on the video was the normal radio interference between the microphone from the GSM module and this other GSM unit here. Let's see an incoming call this time. And let's take this one. I'm gonna activate the loudspeaker again. I will reject this call. And this time I'm gonna dial again, but I'm gonna hide the number. So basically the iPhone is not sending its number. And as you can see, the system is showing withheld number because it's not detecting any caller ID. As soon as I take the call, I have this counter here, this timer for monitoring the call, and it stops when I'm ending the call. And that's pretty much it. If I want to go back to the main menu, I just have to press here. And now I'm going to show you the next application. Let's take this one here. This is the SMS Texting Application. Here is the text field, and here is the number field. And I can switch between these two here. You can see this green corner here. It's changing when I switch between these two fields. If you wonder why I didn't put a small keyboard here, it's because there's not enough space in this area, and I wanted to still be able to use my fingers. So in order to squeeze 30-40 characters here, they have to be pretty small, and that's why I designed it like this. So I'll just type something. Here's a caps lock. It doesn't matter, it's just for showing some basic stuff, so I can enter some numbers, special characters, and then I'm going to enter the number here. And then press send here. And the message is being sent. And here it is. and that's the SMS that I got. Okay, so now I'm gonna go back to the main menu and share the next application. Next, I'm gonna show you the command terminal application. When I started to work on the software, it soon became very clear that the AVR's flash isn't big enough for all the things I had in mind. And so I thought I could make a small graphic interface and build a command terminal. This way I'm able to input commands from a computer or any other device that's capable of speaking serial. I tested like 90% of all the AT commands. The manual containing the AT commands has like 250 pages, and some of them are awesome. I mean, this module is really like a dream come true for people who want to explore the boundaries of GSM technology. There's so much more you can do with it besides what I can show you in this short video. Just to demonstrate, I can enter any AT command here, manually send an SMS, initialize calls, start up a TCP connection and send data. Everything that's in the manual I can enter here. And I'll show you just a command or two. As you can see, I'm using the terminal on my computer. The system communicates over USB, and I use the display to visualize the requests and the answers. That's useful when you're not using a computer to issue these commands. Let's say you have a small keyboard that can interface with it, or like another microcontroller, another system, and they speak to each other. Back to the main menu. Here's a schematic. It's just an image of the pin descriptions for the 6 and 10 pin headers. It could be useful if you're in a situation where you can't look at the backside of the PCB, if you've put the board in an enclosure or mounted it on a panel. And this is a small system info. I've listed a couple of parameters here. The temperature, which is read from the internal temperature sensor of the GSM module. I'll use the solder station to warm the module. You can see the temperature rising. Here it is. VDD. If you're running the module from a battery, it can be useful to adjust its behavior based on this voltage. Shut the system down or put it in sleep mode, issue a warning to recharge the battery. I mentioned earlier that this kind of power management functions are also available via AT commands. That's the signal strength. I don't have very good signal here in this room where I'm filming. And that's the RTC. To go back, I just touch anywhere. Now let's access this configuration menu. And there are two options here. I can set the current date and time. And I can either re-enter the values or accept them. And this is perhaps the most important thing in this whole software, and basically the reason I designed this system in the first place. This application transforms the board into a very high-range control system. Let's say you have this system installed in your home. You can place all kinds of sensors for temperature, humidity, smoke detectors, proximity sensors, and so on and so forth. You can read their status anytime you want. You can set the system to alert you if it's raining or if the temperature is too low, for instance. And you can also control things by connecting relays or motors or water pumps, cat feeders, whatever you need. For instance, you can turn on the heating system before you arrive home and make it warm and cozy. And you can do this from anywhere in the world. If you live in, let's say, Texas, USA, and you want to monitor and control your house while you're in Australia, or any other place in the world that has GSM coverage, you can do that. And you only need your cell phone. You don't need an internet connection, computer, or other systems. There are two different ways you can connect hardware to this system. You can use the 10-pin connector, which provides access to 8 I/O lines. And if you want to interact with more than 8 devices, you can use an extended mode via UART and control thousands of outputs and monitor as many inputs you want. I'll start with the direct interface and then I'll show you the extended UART mode. Now if I go here, you have different ways to report status and take action. You can set it to report the status every 10, 30 or 60 minutes, manually ask for a report, or it can inform you as soon as something's changed, like if someone opened the door or broke a window, if it's too cold outside, you know. And also I can activate output control based on the message you send. You can either check all or only one of these modes. They all work independently. But first, as a security measure, I made it ask for a master number. So you enter your cell phone number first, and then you're the only one that can access the system. I could also implement other security layers like ask for a password or encrypt the message if you worry about spoofing or things like that. First I check if there's a master number set, then I'll enter this iPhone's number. And now I'll go back to the control menu. And I'll activate report on command, report on event, and also control on command. Now the system is active. Let's test it. I've built this small extension board for this demonstration for the 4 inputs, and on this other board here I have 4 outputs, 2 normal light bulbs and 2 main sockets. So there are 4 relays, 1 for each output, and I can't connect anything I want here. I use the light bulbs just to show you the idea. You can make fresh coffee if you want, or turn on the air conditioner. I'll plug this hair dryer and the hand mixer in the main sockets, and here's how to manually control it. Now let's change the inputs, the temperature for instance. This analog circuitry here is setting a threshold voltage. So when the temperature is rising above that threshold, the output is going to go high, and when the temperature is dropping back, the output will return to low. And this is connected to the first input E6, and the system will inform me as soon as this happens. Now I'll deactivate automatic reporting on event, and I'll manually ask what's the pin status. And for this I'm going to change both switches here. I'm going to flip them. Or I could just wait and receive an automatic report every, let's say, 10 or 30 minutes. Now let's change the outputs. I just have to send command followed by a binary sequence. In this case, this light will stay off, this will turn on, the hand mixer will turn on, and the hairdryer will remain off. And I can of course manually override any time. Now about that extended mode for connecting many other inputs and outputs, all I have to do is to send a message like this. This sequence is a hexadecimal number, so it can hold a value from 4 zeros to FFFF. And the idea is that I'm using all these extension boards on a single UART bus. I can use some of the 4 characters to select the address of the board I'm going to speak to, and the other remaining characters to manipulate the outputs. If I use 2 characters for address, that will give 256 combinations, and the remaining 2 characters for the outputs, so that's maximum FF, which is 8-bit. So I can control up to 256 boards multiplied with 8 outputs on each board. That gives 2048 outputs in this case, or relays or motors, light bulbs, by only using 4 characters. And of course I can change this easily in the software and increase this number. If I want to read the inputs too, not a problem. There's no limit on how many you can have on each extension board. So if I send, for instance, UART command followed by 1AD7, that will select the 27th device and then change 8 output pins like this. Because this binary sequence is D7 if you convert it to hexadecimal. And there's a lot of stuff you can do. You can serialize the software for these boards, use jumpers to implement hardware addressing. 8 bits are enough to generate 256 different addresses. Here's a small AVR platform I made a few years ago. I could use this whole port for address and this other one for the outputs, and I still have 6 pins for the inputs. There still are some tricky issues here when using multiple devices on a single UART bus. Error correction, and you have to avoid collisions on the DX line. There are several methods I use for that. You can do it both in software or hardware. You can also use differential signaling, RS422 drivers for instance, if you want to increase the range. And this concludes this demonstration. I hope you enjoyed it. Maybe discovered 1 or 2 new things. I would be glad to hear that. If you have any feedback, like critics, comments, or questions, you can post them below and I'll try to answer that. Also, if you are interested in this system, you can email me. I'm gonna make it available for sale very soon, and maybe I'm gonna also offer custom versions for dedicated needs and purposes. Just feel free to contact me. Until next time, have fun with your projects, have a nice day, and thanks for watching.